Hi. So in our last discussion, we simulated using Microsoft Excel how a one locus two allele selection case behaves. And before we go forward, I would like to say that some of you might have found it a little difficult to follow me and create the Excel sheet the way we did it. So for those people, you can actually go to this website. This is the one where we had gone previously to simulate Hardy-Weinberg. So I'll quickly take you over there. So you can go here and you can say start, and then go to individual simulations. Remember, we are assuming that all other conditions of Hardy-Weinberg are operative, so we will take population size as infinite. Number of generations, actually, as we saw, 200 or so is good enough, so we'll keep that here. And then you have to go to additional settings and go to selection, and then you are going to have all these fitness coefficients for A1, 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 A2 and A2, A2. Set these and you will be good to go. So let's say we'll put at 0.6 and we will put this at 0.9, and let's say we put this as whatever 4, and just say run simulation, and you will be able to see the frequency of the alleles as well as the frequency of the genotypes. Okay. So everything that we did with our Microsoft Excel simulation you will be able to do over here. I would still recommend that if possible try to do the Excel thing, because that way you actually understand step by step how the process is happening. And I mean, while this kind of simulators are very convenient from a teaching perspective, they don't really give you the same level of intimacy with the subject the way hand coded thing like the one we did it Microsoft Excel does. So this is only for those people who are finding it difficult to work on a spreadsheet. They can look at this one. Okay, so let's get back to our PowerPoint. So in our last discussion, we said that we made a bunch of observations from our Excel simulations, and we said that in order to understand those observations in greater detail, we will need to analytically figure out what's really happening in the one locus two allele selection case. So I'm going to analytically derive the expression, and I'm going to draw various kinds of graphs and mathematically show what the dynamics is likely to be under different situations. Now, quite frankly, this particular discussion that we are having today is probably, mathematically speaking, the most involved discussion in the whole 30 hours that we are going to spend together. This particular derivation is slightly advanced in the sense that most regular textbooks of evolutionary biology don't carry it. It's only the slightly more theoretically oriented books, and then also not all of them, who show this particular derivation. It would have been very easy for me to just give you the formula and then request you to take it on faith and go from there. But my personal experience of teaching this for many years at IISER Pune is that until and unless you actually see where the derivation is coming from and what kind of assumptions are being made at various places, you don't really get the feel for the whole thing. So I'm going to do the derivation. This is going to require one or two very basic concepts in algebra and a little bit of calculus, a very little bit of understanding of probability. I will try to explain it in as much of detail as simply as possible. I am trying to aim for those people who might have taken a course in maths in class 12th, or maybe they took their last course in class maths course in class 10th, but they are still not afraid of the maths thingy, and therefore they would like to follow what I am trying to do. Just in case this derivation it seems somewhere in the middle that it's a little too tough for you, or too many concepts you are not really figuring out how I am getting there, I would still request you to go ahead and see what are the main results that are coming. And in case even that becomes too difficult for you, don't bother too much. Okay. In the next discussion, I will actually start that discussion with the result that I am getting today, and I am going to discuss the implications of those results without going into the maths part of it. But as I said, evolution is one of the most highly formalized subject, mathematically formalized subject in whole of biology. So understanding this particular derivation and where it is coming from is actually going to be very, very useful, and which is the reason for which I am going to great length to present it over here. So in order to do this, we will head to a different software. This is Microsoft Whiteboard. And okay, so before we even start doing the derivation, there is one little concept that I have found people often, students, they have a little bit of an issue in comprehending that. People who have done a course in algebra, for them it's not really an issue, but for others sometimes it is an issue. So I'll just present this thing for you over here. So suppose you have okay, let me slightly increase the, yeah, this is good. Let us say you have 5 numbers, 4, 4, 4, 5 and 5. Okay. So 4 3 times, 5 2 times, and I tell you that please take the average of this. What will you do? You are going to do 4 plus 4 plus 4 plus 5 plus 5, and since there are 5 numbers over here in total, you are going to divide the whole thing by 5, and that is going to be your average, right? Now I can write this thing as 3 times 4 plus 2 times 5 divided by 5, right? 3 times 4 plus 2 times 5, which I can write as 3 by 5 into 4 plus 2 by 5 into 5, right? Which I can further write, think about it. What is 3 by 5? 3 by 5 is the number of times 4 is there in this entire sample. In other words, 3 by 5 is the frequency of 4, and similarly 2 by 5 is the frequency of 5. Therefore, I can write this as frequency of a value multiplied by that value itself, and then this entire thing, this is the summation sign, this entire thing summed over all values, right? In other words, if you have a bunch of numbers and you need to take their average, all you need to do is to figure out the frequency of each number and then multiply that number with the corresponding frequency and add them all up, add all these products, and that is going to be your average, right? Very, very simple concept, but this is a concept that is worth keeping in mind before we start this entire thing. Okay, so the main derivation starts now. So we are talking about the one locus, 2 allele selection. Okay, and if you remember yesterday that I said that we are explicitly talking about the viability selection model. Viability selection, right? So what are our 2 alleles? Let us assume that the alleles are A1 and A2, and these alleles, let us further assume that their frequencies are P and Q, where Q is 1 minus P. So, we will be going back and forth between Q and 1 minus P. Okay. So, this obviously leads to 3 different genotypes A1 A1, A1 A2 and A2 A2, right. So, these are my genotypes, and remember these genotypes before selection, their frequencies are P square, 2PQ and Q square, right. So, these are genotypic frequencies before selection. Okay. Now, we have selection happening and we have explicitly viability selection happening. What does it mean? That means that each of these 3 genotypes, they have a different fitness. Let us call them W11, W12, W22, and okay, let me slightly increase the point of the pen. Yeah, let us W11, W12, W22, and these are the fraction of the genotype that is surviving, right. So, the progeny has been born and now they are surviving while they are going to adulthood, and each genotype has a slightly different survivorship, and those are the ones that are being given by W11, W12 and W22. So, these are our genotypic genotypic fitnesses, right. Now, if this be the case, what are the frequencies after the selection? So, after selection, the frequencies are P square W11, 2PQ W12 and Q square W22, right. So, these are genotypic frequencies post selection, right. Now, as we saw yesterday during the simulation, these things are not going to sum to 1, and therefore, we need to do some scaling so that all these 3 frequencies, they sum to 1. What is that scaling? That scaling is essentially dividing each one of them by this sum. Now, this sum we are going to, what is this sum? This is P square W11 plus 2PQ W12 plus Q square W22, right. Now, what is this? As you can see, these are the values of the genotypic fitnesses multiplied by the corresponding frequencies, right. So, if that be the case, these, by what we discussed just now, these are the average genotypic fitness in the population. In other words, W bar, which is this sum, is equal to P square W11 plus 2PQ W12 plus Q square W22, and that is the average genotypic fitness, right. So, therefore, this is unscaled, what we have over here, and the scaled fitnesses, these are P square W11 by W bar, 2PQ by W bar and Q square W22 by W bar, right. Now, before we proceed forward, it is actually going to be very useful for us to derive a certain quantity, okay, a certain concept, and that concept is the concept of the marginal allelic fitness. Now, what the hell do I mean by that? Now, think about it. Fitnesses are actually never derived at the allelic level. Fitnesses are defined at the genotypic level. Okay, A1's fitness, A2's fitness, A1's fitness, and so on and so forth. So, what do I even mean by saying that I want to look at the fitness of an allele? So here we borrow a concept from the subject of economics, and the concept is that of a marginal value. What it essentially means is the marginal allelic fitness is the fitness of all the average fitness of all the individuals in the population who contain at least one allele A1. Okay. In other words, let us see. So, marginal allelic fitness, marginal allelic fitness is the average over average fitness of all individuals who have at least one A1 allele. This is marginal allelic fitness for A1. Okay, at least one A1 allele. Now, how do I get to this? Which are the genotypes which have at least one A1 allele? A1A1 and A1A2, right? A2A2 has no A1 allele, so forget about it. Now, what is the genotypic fitness of A1A1? That is W11. What is the genotypic fitness of A1A2? That is W12, right? Now, we have to do the average fitness. For this, we have to somehow scale it with some measure of frequency. How do we get there? Now, think about the definition. The definition says average fitness of all individuals who have at least one A1 allele, right? So, let us say that this A1 allele is fixed, right? Now, if one allele is fixed as A1, we have already picked it up. What is the probability, assuming random mating of course, what is the probability that the other allele that you pick is also going to be A1? Under the Hardy-Weinberg conditions, which is where we are operating in over here, that is equal to the frequency of the allele A1. In other words, that is equal to P. Similarly, assuming that one allele already has been picked up as A1, what is the probability that the other allele is going to be A2? And that probability is simply Q. So, W1 star, which is the marginal allelic fitness of allele A1, is equal to PW11 plus QW12. Okay. Similarly, let us think about the marginal allelic fitness of allele A2, which is W2 star, equal to what is going to happen? Which are the two genotypes which have A2? One is A1A2, the other is A2A2, right? So, in this, the genotypic fitness of this is W12, genotypic fitness of this is W22, right? Now, given that one allele has been fixed as A2, what is the probability that the other allele is A1? That is equal to the frequency of A1, which is P. Similarly, given that one allele is A2, what is the probability that the other allele is also A2? That is equal to the frequency of A2, which is Q, right? So, the sum, in other words, W2 star is equal to PW12 plus QW22. Okay. These two quantities, although it is not entirely clear to you as of this moment why we need these two quantities, it will become clear in a few minutes. So, in order to figure out what really is happening, we come back over here and we start looking at this W bar. Okay. So, we said this W bar is equal to P square W11 plus 2 PQ W12 plus Q square W22. Now, I can write this as W bar is equal to P square W11 plus the 2 PQ W12, I will break it up as PQ W12 plus Q another PQ W12, okay, just writing it in two parts, plus Q square W22, right, equal to, this is there is a P here, there is a P here, I will take the P as a common. So, P common PW11 plus QW12 plus here I will take Q common PW12 plus QW22, right. And if you just look at what we derived 1 second earlier, PW11 plus QW12 is W1 star and PW12 plus QW22 is W2 star. So, if we come back over here, this simply becomes equal to PW1 star plus QW2 star, right. This is my W bar. This is another thing that we need to keep in mind, right. Now, let us keep a third thing in mind. We again go back to this definition of W bar, and now let us start writing it, in terms of P. So, what are you going to do? So, W bar is equal to P square W11 plus this is 2PQW12, right. So, 2P and Q I will write it as 1 minus P, okay, W12 plus Q square W22. So, Q square I will write it as 1 minus P whole square W22, easy, equal to, I will expand it, P square W11 plus 2PW12 plus, or rather minus 2P square W12 plus, so 1 minus P whole square is 1 minus 2P plus P square. So, 1 into W22 is plus W22 minus 2P from inside into W22 minus 2P into W22 plus P square W22, P square into W22, simple algebraic expansion, nothing else, equal to yeah, okay, actually this is fine. Now, I want to know how W bar changes with change in P, okay. Now, in order to know that, from calculus we know that we need to look at the quantity dW bar by dP, right. So, we are going to differentiate this with respect to P. Now, if you have forgotten differentiation, just take it from me that hopefully what I will do is correct. So, 2P W11 plus 2W12 minus 4P W12, this W22 goes away, minus 2W22 plus 2P W22, right. Now, if you remember your calculus, you can see that there should be a few extra terms which I am not putting over here. Why am I not putting them? Because I am explicitly assuming that the W11s, W12s and W22s, all these are constant. In other words, I am explicitly assuming that these things do not vary with P. If I did not make that assumption, then I would have to add 3 extra terms over here. We will come to that towards the end of today's discussion, but as of this moment we are going to assume that all these W11, W12 etc., these are frequency independent. So, what we are explicitly assuming is that there is frequency independent selection happening, okay. Frequency independent means that W bars, the values of W11, W12, W22, they do not depend on P. So, if that be the case, let us go forward. this is my dW bar dP. Now I can write this dW bar dP is equal to, see I have a 2 everywhere, right. So I will just take this 2 outside and this becomes Pw11 plus W12 minus, so I have taken 2 outside, so I have 2 Pw12 inside. So this 2 Pw12 I will write this as minus Pw12 and I will again write it as minus Pw12. Okay, 2 has gone outside, 2 Pw12 remains. I have split it into minus Pw12 minus Pw12 minus Pw12, and then 2 has gone outside, so I have minus W22. 2 has gone outside, so I have plus Pw22 bracket closed, right, equal to 2 outside, Pw11 is fine, plus, so this is W12 and W12 over here. So I can take the W12 common, W12 1 minus P, right. So this term is done, this term is done, this term is done. I will take the minus outside and this will become Pw12 plus W22 minus Pw22. Okay. Now let's equal to 2, this is Pw11 and 1 minus P is Q, so this is plus Qw12 minus, I have Pw12 over here and I have W22 minus Pw22, I can take W22 common over here, then this will become W22 into 1 minus P, which basically means Qw22. In other words, I have Pw12 plus Qw22, right, equal to, I think you can already see where this is going, Pw11 plus Qw12 remember is W1 star. So equal to 2 W1 star minus W2 star, right. This is the third relationship that we need to develop, that dW bar dP is equal to 2 W1 star minus W2 star, assuming that our genotypic fitnesses are frequency independent. Again, I cannot stress this enough. This is assuming frequency independent selection. Great. So now that we have these things, let's come back to our main stuff. Remember, we started with trying to figure out the recursion of P due to selection across generations. So these are the things that we have got. So now allele frequency in next generation, okay, in the among the offspring, that is, what is that? We will call that as P hat, P prime is equal to, how are you going to get it? Remember, this is my capital P, this is my capital Q, then P prime is simply P plus half Q. In other words, P prime is equal to P square W11 by W bar plus half of this 2PQ by W bar. In other words, I will write it as PQ by W bar. Okay. Now equal to, W bar is the common denominator, so W bar is my common denominator, equal to, I will take the P outside, Pw11 plus, sorry, there is a PQ12 over here, okay, Pw11 plus Qw12 whole by W bar. Again, the stuff inside over here, you can see this is W1 star. So, equal to P into W1 star by W bar. This is my next generation allele frequency. Now, suppose I want to look at the change in allele frequency. In other words, I want to look at delta P, which is defined here as P dash minus P. Okay. By how much has selection been able to change the allele frequency over one generation? Great. So, what is that value going to be? So, we just saw that P prime is this. So, delta P is equal to P W1 star by W bar minus P, equal to P W1 star minus P W bar divided by W bar, or I can take the P outside, P by W bar W1 star minus W bar. Okay. Now, if you remember, we at some point when we were looking at our expressions, we saw that W bar is equal to PW1 star plus QW2 star, right? We have already kept this one over here. So, we will import that one over here, equal to P by W bar W1 star minus P W1 star minus QW2 star, right, equal to, let's take it a bit forward, equal to P by W bar. This is W1 star minus PW1 star. I can take the W1 star common. In other words, this one will become W1 star into 1 minus P, which is QW1 star. So, equal to QW1 star minus QW2 star, equal to, I can take the PQ, I can take the Q outside, equal to PQ by W bar W1 star minus W2 star. Now, if you remember, when we were talking about dW bar dP, we derived that dW bar dP equal to 2W1 star minus W2 star under the frequency independent condition. In other words, from this we can see that W1 star minus W2 star is equal to half of dW bar dP, right. So, now I can take this relationship over here and I can put it over here and say that delta P is equal to PQ by W bar, there is a half, so I will put a 2 over here, into dW bar dP, right. This is one of the most famous equations in evolutionary biology, known as Seville-Wright's equation for fitness landscape. Okay. Sometimes people take it one step forward, and what they do is, okay, let me do it over here. They write this as delta P is equal to PQ by 2 d of ln, where ln is the natural logarithm, ln W bar dP. Okay. The reason this works is because d ln W bar is equal to 1 by W bar dW bar. So, this is also another form in which the equation is often talked about, although this is the form in which we are going to analyze it. Okay. So, Why is this equation so important? Why is this, I'm saying it's one of the most famous equations. To understand the implications of this equation, what we first need to do is to just look at its structure. So see that it has P, it has Q, it has W bar over here. What is P? P is an allele frequency. So we know that it will lie between 0 and 1, which means it's positive. Similarly, Q, 1 minus P, will also lie between 0 and 1, which means it's positive. W bar is the average genotypic fitness, which basically means this is average of lots of values, each one of which is between 0 and 1. So, average of lots of positive values means itself it's going to be positive. Therefore, this stuff over here, whatever is inside this circle, this thing is always positive. That implies that the sign of delta P is going to be equal to the sign of dw bar P. Now, what is delta P? Remember, delta P is P dash minus P, which means by how much is the allele frequency changing in one generation due to selection. So, what this is saying is that the sign of that is going to be the same as the sign of dw bar dp. Now, what exactly do I mean by that statement? What I mean by that statement is that if you end up having P on x axis and W bar on y axis, then you are going to get some kind of a graph, and we will talk about it in a few minutes what kind of a graph you will get. But that graph, it's let us say you will get it something like this, or let us assume that you end up getting something like this, whatever, you can get all kinds of shapes, okay. But whatever you get, for any value of P, the sign of delta P, in other words, whether P will increase in this direction or P will decrease in this direction, that is going to depend on the slope of this particular curve at that point, okay. If the slope is positive, delta P is positive, P will increase. If the slope is negative, delta P is negative, P will decrease, okay. Now, let us further examine this W bar. It is a fantastic thing. So, we started by saying that this is our W bar, right? P square W11 plus, let me reduce the size a bit, P square W11 plus 2PQ W12 plus Q square W22. Now, as you can see, this is quadratic in P. What do I mean by that? What I mean is that the powers of P, the max power that P can have is 2, right? It can't go beyond a square. Now, we also know that if you have a quadratic, then that quadratic is going to have at max one maxima or one minima, right? And that maxima or minima is going to happen when dw bar dp is equal to 0. Now, what is the meaning of dw bar dp is equal to 0? The meaning of dw bar dp is equal to 0 is that the allele frequency is not changing. It has gone to an equilibrium, right? Now, what are the ways in which this equation can go to an equilibrium? So, if you think about it, this equation can go to an equilibrium. So, this is P, right? So, P is going from 0 to 1, right? So, when P is equal to 0, that means that P equal to 0 means that Q is equal to 1, which means that the entire population is full of A2 individuals, right? There are no A1 individual, there are no A1 A2 individual. So, if that be the case, at this point the average genotypic fitness of the population is basically just W22, because there are no other individuals. Similarly, when P is equal to 1 and Q is equal to 0, what will happen? You only have A1 individuals in the population, there are no A1 A2, there are no A2 A2. In other words, at this point W bar is going to be equal to W11. Here W bar is going to be equal to W22, right. So that point on this axis can lie anywhere. Similarly, over here, it can lie anywhere. These are the two fixed points. Once the population has gone here, either fixed for allele A1 or fixed for allele A2, nothing can change. But barring those 2 points, what is going to happen in the middle for intrinsic values of P? Now, suppose you have a scenario like this, where the slope of this curve is always positive. Then, as I said, delta P is always going to be positive. In other words, P will always increase and you will get a fixed point over here at P, P equal to 1. Similarly, if you have a scenario which looks something like this, you are going to have equilibrium here at P is equal to 0. It will go like this. Okay. But I mean, these are the things that we saw yesterday, right? We saw that for many cases, the allele frequencies were either at equilibrium, were either going to 0 or going to 1, depending on who had a higher fitness. However, we did end up seeing certain situations wherein the allele frequency was going to an equilibrium at an intermediate value of P. In other words, some P which was between 0 and 1. So, at these positions, dw bar dp is going to be equal to 0. Now, if dw bar dp is going to be equal to 0, we have already figured out that dw bar dp is equal to 2w1 star minus w2 star, which means that at equilibrium, 2w1 star minus w2 star will be equal to 0. In other words, w1 star will be equal to w2 star. Now, what is the formula for w1 star and w2 star? So, remember, let me just get this above. Remember, Pw11 plus Qw12, that is my w2 star, will become equal to Pw12 plus Qw22, that is my w2 star. So, let me collect all the P's and the Q's on one side. So, Pw11 minus Pw12 is going to be equal to Qw22 minus Qw12. So, I take P as common, W11 minus W12 is equal to, I take Q as common, W22 minus W12, right, at equilibrium. Remember, that is the condition we are dealing here. Now, think about it. P, as we just discussed, is an allele frequency, so it is always positive. Q, as we just discussed, is an allele frequency, so always positive. Therefore, forget about the magnitude, just think in terms of the sign. The sign has to be equal on both sides, right? So, this relationship in terms of its sign can be true if and only if W11 and W1 and W22, either both of them are greater than W12 or W11 and W22, both of them are less than W12. Why am I saying that? Because let us take the first condition. W11 is greater than W12, so this is positive. W22 is greater than W12, so this is positive, 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 great. But suppose that is not the case, then you will have positive on one side and negative on the other side, which cannot happen, right. Therefore, this W11, W22 both being greater than 12, W12 will ensure that you are having a positive sign on both sides. Similarly, if W11 is less than W12, you are going to get a negative sign over here. W22 is less than W12, you will get a negative sign over here. However, if you have a scenario where W11 is greater than W12 is greater than W22 or the other way around, then this is not going to work out. You are not going to get an internal equilibrium, right. Now, great. So, we now know the conditions that will lead to these equilibriums. But remember, we are dealing with a quadratic form. In other words, our equation or graph is going to be a parabola. Now, a parabola we know can either have a maxima or it can have a minima. Now, knowing this does not allow us to tell which one is which one, right. So, in which case we are going to get a maxima, which case we are going to get a minima, that is not entirely clear. So, in order to figure that out, what do we need to do? We simply need to take a double differentiation, right. So, we will start from this point, okay. So, we will differentiate this again, sorry, d2 w bar by dp square equal to, we will take the keep the 2 aside, okay. This is going to be equal to w11 this w12 will go, remember this is 2p w12, so this is minus 2 w12 and this w22 will go, plus p w22 means plus w22, right. So, this is my double differential. So, we know that when this double differential is negative, that is when we are going to get a maxima, and when this double differential is positive, that is when we are going to get a minima. This is what calculus tells us, right. When is this thing going to be positive? This thing is going to be positive when both w11 and w22, when both of them are going to be greater than w12. So, this case, right. So, when w11 and w22 both are greater than w12, then we expect a minima, and similarly when w11 and w22 both are less than w12, we expect a maxima, right. So, with this knowledge, now let us start plotting. So, as I said, you can have 3 kinds of graphs over here, okay. In all these graphs, we have P, the allele frequency of allele A1 on x axis, and we have W bar on the y axis, okay. You can have a situation where the thing is negative or positive throughout, the slope is negative or positive throughout, and in all those cases, irrespective of where you start, your P, your dw by dp is always going to be positive or always going to be negative, and therefore, P will either go in this direction and get fixed at 1, or it will go in this direction and get fixed at 0, okay, 0. So, this is 0 and this is 1. If you have a situation which is like this, w11, w22 is greater than w12, then you will get a graph which will look like this, okay. The minima will be somewhere in the middle, and this situation where w11, w22 is greater than w12, this means that the heterozygous form is less fit than both homozygous forms. This is what is known as underdominance, okay. This is the case where w11, w22 is greater than w12, and this situation where the heterozygous has the maximum fitness and compared to the 2 homozygous conditions, this is the case where you will get something like this, okay, where you are going to get a maxima somewhere in the middle. Now, obviously these points, these are the points at which dw bar dp is equal to 0. In other words, these are the points at which P has stopped changing. These are equilibrium points. However, there is a qualitative difference between the nature of these 2 equilibrium points. Why that is so? Let us see. Let us first start with this one. In this particular case, what is happening? On the left side, the slope of this curve is positive, at all the points, right. So, slope means dw bar dp. So, dw bar dp is positive to the left, is greater than 0 to the left, and it is less than 0, dw by dp is less than 0 to the right. Therefore, what did I say about delta p? Delta p will have the same sign as dw by dp. So, on this side delta p is positive, which means if the allele frequency is anywhere in this zone, it will go here. Okay. Whereas, this side it is negative. So, if the allele frequency is anywhere in this zone, it will go in this direction, right. Now, what happens when the allele frequency goes like this? This is W bar, right. So, the population, the average genotypic fitness of the population will go like this for this side, and on this side it will go like this, like this, right. Now, what exactly happens over here? As we said, this is an equilibrium point, but once you have reached this point, if you slightly perturb the system, if you slightly change the allele frequencies, it will come back to this, stating that this is a stable equilibrium point. Okay. I forgot to tell you that the situation where the heterozygous the condition is the most fit, this is what is called overdominance. These are technical terms, overdominance and underdominance. Great. So, in other words, in this situation the fitness is always increasing. Now, what is going to happen over here? In this case, again this is an equilibrium point, but the slope of dw by dp is positive on the right hand side. So, if you slightly perturb the system is going to go in this direction over here till it hits 1, or if you start perturb it in this on this side of this equilibrium point, it will go in this direction and it will hit 0. In both cases, what happens to the average fitness? The average fitness in both cases goes up, right. Even in this case, the average fitness is going to go up. Okay. What happens here in this particular case? Here, if you see that the slope is positive over here, so any point where you start, the average fitness will go like this, right, because delta p is always positive. So, p will go in this direction, so it will go like this, and for the other one this is negative, and therefore, it will the average fitness will go like this, delta p will keep on reducing, and the average fitness will go like this. In other words, in all the graphs that we are seeing, we see that the average fitness of the population is always going to go up. Okay. And this is what leads to the thought process in the minds of most people, that the beauty of selection is that it is always going to increase the average fitness of the population. That is what selection does. Okay. Note that that intuition is mathematically well supported, but it is well supported only in this scenario that we are talking about, the 1 locus 2 allele scenario under the frequency independent selection case. Now, as you can guess, if I am stressing on this, harping on this so much, then obviously that there has to be a twist in the tail. What is the twist in the tail? The twist in the tail is related to this thing that we did over here. Okay. We said that because this is frequency independent, therefore we are dropping 3 terms. Okay. What are the 3 terms that we dropped? So, let us now go to that scenario. Let us go to the scenario that where you have the frequency dependent case. Okay. Frequency dependent genotypic fitness. Now, we are looking at dw bar dp, okay, and all the terms that we did over here, each one of these terms, they will all exist, and therefore we are going to get the final thing that we got, which is equal to 2 w1 star minus w2 star. This part is constant, I mean the similar. However, On top of that, there will be 3 other terms. What are those 3 terms? Remember, now we are explicitly assuming that these things, these 3 genotypic fitnesses are function of P themselves, and therefore the 3 terms are going to be P square dW11 dP plus 2PQ dW12 dP plus Q square dW22 dP. Okay, this is the rule of differentiation. Now look at these 3 terms. What are they? These 3 terms are 3 differentials, the differentials of the corresponding genotypic fitnesses multiplied by their corresponding frequencies, right? Therefore, this itself, these 3 terms together, they form an average of what? An average of the genotypic fitnesses. So this, or rather the derivatives, average of the derivatives of the genotypic fitnesses. So this can be written as 2 W1 star minus W2 star plus average, can in statistical sense is also known as the expectation of dW dP. Note, this is not dW bar, expectation of dW dP, which essentially means the average over these 3 derivatives of these 3 genotypic fitnesses, right. So if this be the case, then remember we need this stuff, right. So then W1 star minus W2 star is going to be equal to half of this, goes this side, right. So this will become half of dW bar dP minus expectation of dW dP. Okay, and this, now we have to superimpose this stuff on okay, where are we? Just one second. Ouch. Okay, so yeah, so this is where this gets superimposed. So delta P, so let me write it proper way. So for the frequency dependent selection, delta P is equal to PQ by 2, this part stays the same, PQ by 2 expectation PQ by 2 W bar, sorry, dW bar dP minus expectation of dW dP, right. Now here comes the first big major problem. What is the problem? The problem is that it's not at all clear that these 2 terms will go to 0 at the same point. In other words, when dW bar dP will go to equal to 0, it's absolutely not certain that dW dP should also go to 0. In fact, in many cases it will not. Therefore, dW bar dP going to 0 doesn't necessarily mean that your delta P has gone to 0. In other words, you have a situation where it's not entirely clear that you will definitely get a internal equilibrium. In many cases, what you actually end up getting is all kinds of complicated dynamics, including oscillatory dynamics. In other words, it doesn't settle to an internal equilibrium. The fitness doesn't always increase, sometimes it increases, sometimes it decreases. And under this situation, you can also have scenarios wherein due to selection, the average fitness of the population will keep on decreasing, finally leading to extinction, a phenomena which is technically known as Darwinian extinction, right? Now just think about what we are saying. We are saying that when you have the one locus two allele selection case, then under frequency independent selection, frequency independent genotypic fitnesses, selection can increase the population fitness, average population fitness. However, even under the simplistic one locus two allele case, the moment the fitness itself, genotypic fitness itself becomes dependent on frequencies, this is not going to happen. And you can get a situation where selection leads to way more complicated dynamics, oscillatory dynamics, or even extinction. And this is with one locus. The moment you go to two loci or more than two loci, the interaction of selection actually becomes very, very complicated. This is why I wanted to show you guys this particular derivation, because if you talk to any normal person, even biologists, forget about non-scientists, even scientists, we have this implicit notion in our head that selection will always improve the species, selection or the population, selection will always increase fitness. That entirely comes from this simplistic Wright's equation, which is this one. The moment you go out even slightly of that simplistic, highly restrictive scenario, you are no longer guaranteed that selection is going to increase fitness. Selection can do many, many things. And people like us who actually work with selection and experimental evolution in our lab, we actually know how complicated a thing selection can be. Okay, so it's only under the simplest scenarios that selection improves fitness. Under even slightly more complicated scenarios, selection doesn't really improve fitness all the time. It improves fitness many times, or at least some of the times, but definitely not all the times. So we are going to stop over here, and when we come back for our next discussion, we are going to ask what are the implications of this, and I am going to start that discussion with some of the insights that we are getting over here, and we'll probably, let me see if we have time, we'll quickly do some Excel simulations to drive home some of these points that we are making, and we will explicitly answer the 3 or 4 observations that we had last time, and we'll explicitly answer why those observations are the way they are. In fact, if you just take today's discussion and go back to those observations, the answers should become very clear to you. But for the sake of those people who are finding the maths a little tough, I will end up discussing those explicitly in the next discussion. See you.